Hi everyone, my name is Kun-Ting, and today I will give a brief presentation about my PhD work. The topic is structural and electrolyte effects in cathodic reaction at platinum-based electrocatalysts. Here's the list of my publication during the studies, and I will select one of the main work today to present. First of all, let me briefly introduce the basic idea of hydrogen economic. As we know that global warming is a severe environmental issue nowadays, to create a sustainable lifestyle is quite important. One of the ways to use energy generated from the renewable sources. This energy is used to produce the so-called green hydrogen by water splitting. And the hydrogen is applied to the fuel cell as an energy source to generate electricity for our daily consumption. In addition, the basic working principle of the PEM electrolysis and the fuel cell are written on the right-hand side here. Basically, the total reaction of the electrolysis is to split water into hydrogen and oxygen. On the other hand, the reaction of the fuel cell shows the opposite direction. However, the current bottleneck to developing this device is due to the slow oxygen reaction. As the reaction involves the complex and the multi-electron transfer processes, they cause higher over potential and lower the reaction rate. That's why we need to find a good catalyst to improve the reaction kinetics. Furthermore, the basic idea about the catalyst is that from a thermodynamic point of view, the catalyst not only decrease the activation energy of the reaction, but also change the reaction pathway, which can cause different activity, stability, and solubility. In fact, the reaction system at the electrolyte interface are more complex. There are several parameters can influence the reaction of the heterogeneous catalysis. For example, at the electrode surface, factors include the structural effects due to the different coordination number, composition, and the particle size. Besides, the effect due to the interaction between the nanoparticles and the electrode support, as well as the influence of the electrolyte composition, are also plays an important role in reaction performance. Here, the selective principles, the so-called volcano plot, highlight the essential role of the reaction activity and the bonding strength between the electrocatalyst and the reaction intermediate. It says that the binding energy shouldn't be too strong or too weak. If the interaction is too strong, the reaction is limited by the desorption of the product. However, if the binding energy is too weak, the reactant fails to bind to the catalyst and decrease the reaction activity. As you see that platinum shows one of the best catalysts for oxygen reduction reaction in fuel cell, but it still has a slightly too strong binding energy. So there are several factors can influence the performance of the heterogeneous catalysis. In this study, we focus on two factors, which are the surface and electrolyte composition. In the case of the surface composition, the figure shows the relative OR activity as a function of the lattice parameter or the platinum-platinum distance. This bimetallic platinum alloy shows higher activity due to the so-called strength and ligand effect. Here, the strength effect points out the difference in lattice parameter between the atoms in the surface layer and those in the bulk, which can introduce different strength on the electrode surfaces. The ligand effect appears due to the heterometallic bonding interaction of the surface atoms with different neighboring atoms. And both effects can alter in the electronic state of the electrode surfaces. Secondly, the influence of the electrolyte composition. It's reported that the OR on the platinum 111 surface has the lowest activity in lithium OH and the highest in the cesium OH, which is due to the so-called non-covalent interaction between the hydrogen shell and the reaction intermediate. In this work, the reason to use the platinum alloys such as platinum 5-gadolinium and platinum 5-yttrium are to decrease the mass loading and to decrease the binding energy and thus reach the higher activity. And the reason to use to measure the reactions in acidic and alkaline media are because that they are suitable for different types of the fuel cells. Furthermore, different types of the alkali metal cations can serve as a spectator to change the reaction activity as well. So today we focus on this work, the influence of the alkali metal cations on the oxygen reduction activity for platinum 5-ether and platinum 5-gadolinium alloys. First of all, let's talk about their material characterization. By the XRD result of the test sheet, you can see that of the XRD result shows that the test electrode shows the polycrystalline structure, and the lattice parameter alpha can be calculated. Throughout the XPS analysis, it has been proved that there is a platinum overlayer formed on the block after the so-called acid-leaching processes, and therefore the lattice strength can be calculated by the following equation here. Secondly, let's talk about the electrochemical measurements. Through the copper under potential deposition measurement, the electrochemical active surface area can be calculated. The bar chart here on the right-hand side shows the value is very close to the geometrical surface area, which proves again that the formation of the platinum overlayer on the platinum alloys. Furthermore, in acidic media, the platinum alloy shows several times higher OR activities than the pure platinum, which is mainly due to the compressive strength on the electrode surface that decrease the binding energy and then increase the OR activity. Furthermore, let's talk about the OR in the alkaline media. The OR activities for platinum shows the trend that the lithium is the worst and the cesium is the best. However, for platinum alloys demonstrate the opposite trend, in which the OR activity increase with increasing hydrogen shell. The main reason is that the structural making cations like lithium and sodium ions, which has higher hydrogen energies, can stabilize the slightly weaker binding energy condition of platinum alloys, which makes better reaction condition and increase the reaction rate. On the other hand, the structural breaking cations such as rubidium and cesium ions with lower hydrogen energies can destabilize their non-covalent interaction and cause lower activities. So by combining the factor A and B, which are the electrode and electrolyte compositions, we use the density function theory to simulate the situation, which considers the sorption energy of the OH intermediate on the platinum 111 surface under different strengths and cation conditions at the interface. The computational result shows that under higher compressive strength condition, which is noted as a negative sign here, the overpotential of OR decrease in the presence of the lithium ions, while increase for the presence of the cesium ion. The result highly supports the experimental findings for platinum alloys and indicated that not only the strength condition, but also the electrolyte composition should be considered to obtain the highest activity. So in conclusion, in acidic media, due to the induced compressive strength effects on the platinum alloys, the OR activity is higher than pure platinum. Besides, in alkaline media, shown on the right-hand side here, with the procedural volcano plot, with the OR activity as a function of the lattice parameter, the figure shows that as the lattice parameter increase, the compressive strength increase on the platinum alloy surface, and the activity for platinum alloys increase with higher hydrogen energy of the cations. However, the platinum shows the opposite trend. And throughout the experimental and computational results, it's proved that both structural and the electrolyte cations effects needs to be considered to improve the reaction kinetics. In the outlook, we have considered the strength effects on the atomic scale by the corresponding lattice parameter. The other point to be considered is the mechanical strength on the electrode surface. We are trying to deposit a thin film of catalyst on the flexible polymer substrate, which can quantitatively measure the mechanical strength and correlate it to the electrocatalytic performance. For instance, we can deposit platinum and gold to measure the OR activity under different strength conditions, as they're typically situated on a different side of the volcano plot here. And thank you for your attention, and I'm willing to discuss with you if you have further questions.